Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series. In just a minute, I will be thrilled to roll out with you this week's seminar with Elizabeth Bennewitz, and I'm so glad that you could join us today on time. Before we begin with introductions, let's give everyone just about a minute or two to tune into the live stream. Meanwhile, folks, you know my favorite question, which is where's everybody tuning in from today? You can reply to that in the comment chat box on YouTube, which is located somewhere on the right, left, above, or below on your screen. And that's the same place where you can ask questions live during the seminar of Elizabeth. We try to keep this very interactive and have a discussion. Usually we end up with many questions and run a little bit over time. So feel free to use the chat to communicate with each other, discuss, ask questions. I'll try to bring them up to Elizabeth at a good time. You can only do that live during the seminar, but otherwise this talk will stay recorded, so you can always go back and rewatch it. And to find out more about upcoming talks, you can click that subscribe button so you stay up to date with the latest Qiskit seminar series. And I think, folks, it's maybe about time that we get started today. Today, I'm thrilled to roll out the latest episode of the IBM Qiskit Live Quantum Seminar Series, dedicated to you, the research and academic quantum communities. I am your host, Zlatko Minev from IBM Quantum Research, and today I have the special pleasure and privilege of hosting Elizabeth Bennewitz. Elizabeth Bennewitz, who's an advisor at OneQubit and a PhD student at the University of Maryland with Alexei Gorshkov. And before we bring Elizabeth's slides up and Elizabeth here to the stage, I'll begin with a bit of bio. Elizabeth received her bachelor at Baldwin College, her master's degree at Perimeter Institute, and Elizabeth is now a PhD student at the University of Maryland, advised by Alexei Gorshkov. Most recently, Elizabeth is also an incoming fellow at the Department of Energy Computational Science Graduate Fellowship. With that, Elizabeth, it's a pleasure to welcome you to the seminar. How are you doing today?
I'm good. I'm really happy to be here, and thanks for the invitation.
Well, before we get to your slides, I like to start with my favorite question, which is where are you today?
I'm currently in Massachusetts.
All right. Well, greetings from New
Yeah,
York. We can pull up your slides, and the stage is yours.
great. All right. So just to confirm, can you see it all good?
Indeed, I can. Thank you.
Okay, great. Well, thank you everyone for tuning in. I'm really excited to talk to you today about neural error mitigation of near-term quantum simulations. And this is the work that I've done with my fellow co-authors, Florian, Bogdan, Juan, and Puya. And we'll see this soon. It was accepted for publication in Nature Machine Intelligence. And so this method is a machine learning approach to error mitigation. We're really trying to combine some of these attempts of quantum simulation that are done in the quantum setting and combine it with these classical machine learning approaches to quantum simulation. So to give you an outline of my talk, I'm first going to kind of briefly motivate why we're interested in simulating ground states, as well as why we need error mitigation. And then I'll go into kind of one of the core concepts and tools in our error mitigation protocol, which is the idea of a neural quantum state. And then I'll discuss in greater detail what our procedure does and how we're training these neural quantum states for the task of error mitigation. And then I'll kind of wrap it up with some results, so showing you how this method performs on two different models, and then kind of wrap everything up with a summary. So simulating ground states is a really important pursuit because characterizing ground states is really important kind of every aspect of quantum simulation of these different quantum systems. So ground states can encode the behavior of a system at low temperature. It can also express symmetries, which are really important in condensed matter physics. It also can describe the electronic structure of atoms and molecules, which shows up in quantum chemistry and in drug discovery and reaction rates. And so kind of finding accurate and reliable representations of these ground states is a really important kind of fundamental task. Except simulating these ground states or kind of simulating these quantum many-body systems themselves is really hard classically. And that's most notably because these Hilbert spaces scale exponentially, kind of according to your internal degrees of freedom with the number of systems or sites you have. And it's very natural to try to study these problems on quantum computers because they themselves are these quantum systems and can much more efficiently represent the states that we're trying to study. But simulating these kind of ground states in the NISQ era, so in this noisy intermediate scale era, has a lot of promise. Kind of most notably thinking about, we can't even simulate devices of 50 to 100 qubits using classical simulation. So we really kind of expect to see some really interesting results and hopefully unveil new science by kind of studying these ground states and studying quantum simulation tasks on these NISQ devices. And I'm sure you've heard a lot about kind of all of the different hybrid algorithms that people are trying to use these devices on to try to extract and make the most of the utility of these NISQ devices while we can. But these devices are greatly limited by it could be the noise in your system, limiting the depth of your circuit. It could also be kind of the number of shots that you have access to. But we need to develop strategies to improve the output of these devices and really extract as much as we can about from the quantum computation or quantum simulation that we're interested in studying. And so kind of the long-term goal here is that we can implement some sort of quantum error correction and scale that up to study kind of a fault-tolerant quantum computation. But in the meantime, what we can do is develop error mitigation techniques that kind of reduce and mitigate the effects of noise via some sort of classical post-processing technique. And what I've really enjoyed about this error mitigation field is it's really flexible, it's really creative, and kind of you can think about a lot of different ways to manage noise in quantum devices. And so the method that I'm going to be presenting to you today it looks like this, where there's 3 steps, but really I think of the first one as like a 0th step because it needs to be done kind of before we do this error mitigation procedure. So the first kind of 0th step here is that we want to have some sort of ground state prepared on a quantum device. So this could be VQE or variational quantum eigensolver run to convergence. And at the end of this protocol, then you have some noisy approximation of your ground state. It sort of has imperfections in it and isn't as accurate as we want it to be. So the first step that we want to do is translate this ground state that was prepared on the quantum device and translate it into kind of a classical language that we can then post-process. And so the way that we do that is by using kind of a machine learning data-driven approach to quantum state tomography, where tomography in general is trying to solve the problem of state reconstruction. But this is a machine learning approach to that, which is called neural quantum state tomography. So once we've been able to kind of translate the state from the quantum device and store it in the classical neural network, we then are going to do variational energy optimization to that state that we kind of were able to translate and extract from the device. And it's this last step where we're doing variational energy optimization, where we're trying to improve the representation of the ground state of the system that we're trying to study. And so the key kind of tool that we use in our error mitigation procedure is this concept of a neural quantum state. And so this is a neural network that is used as a wave function ansatz. And then we can train it using various different kind of cost functions and training protocols in order to approximate, have an objective to approximate different wave functions. And so I'll discuss kind of in the outline of my talk. I'll first give you a lot more information about these neural quantum states, give you an intuition about what they look like and kind of how we train them. And then I'll discuss the specifics of training this neural quantum state in this first step, so in this tomography step, as well as in this energy optimization step, and show you kind of how they come together to compose an error mitigation protocol. And so it is these last 2 steps, plus a couple of measurements, that really kind of composes and describes our neural error mitigation protocol. So what's really useful kind of and what this method capitalizes on is advances in machine learning and to improve the output of a quantum computation. So there's been a lot of really wonderful work on the classical side of machine learning, where people have started to recognize that, a lot of these cursive dimensionality problems that exist in data science can also be kind of adapted to the study of quantum problems. And so what this method really does is kind of bridge this gap, or kind of combine together quantum approaches to quantum simulation and classical approaches to quantum simulation, and interpret that in the task of an error mitigation protocol. So our method itself is hardware agnostic, which makes it very versatile. We can apply it to different platforms for quantum computation. We can also apply it to kind of different quantum simulation protocols. So it could be that we're trying to study kind of a output of a quantum simulator, and as well as looking at something like a quantum computer itself, which has this universal gate set. And the quantum overhead for this method is kind of just like a simple measurement data set. So there is a really kind of low quantum overhead required on this error mitigation protocol. And it's very versatile. So as I mentioned, it could be applied to various types of quantum simulation algorithms or quantum simulation protocols, and also applied to kind of various different systems where you're trying to find the ground state of some problem. And in this talk, I'll discuss kind of examples from quantum chemistry as well as a lattice gauge theory problem. So so to go into some more detail, I want to talk about this really useful tool, which is this neural quantum state. So to give you a kind of intuition about what these neural networks and what these neural quantum states are, I'm just going to have you look at a very simple one hidden layer neural network. So here you have some n-dimensional input. You have a bunch of weights and nodes in this neural network, and then you have this output function f. And so what you are trying to do in this context is you're trying to get the neural network to be able to predict the function f based off of various inputs. And so when I interpret this wave function or this neural network as a wave function ansatz, what I'm doing is this. I interpret, or I input, my data set is going to be measurement outcomes or computational basis states. And then my output function is the amplitude of that computational basis state. And so I can effectively train these weights, kind of increasing the weight on other ones or minimizing the weight on various different kind of between different nodes in order for the function output to predict a different value. So in this context, as I train these weights, I'm asking the neural network to kind of approximate these, or to learn the amplitudes of some particular wave function that you're trying to learn from some data set. So kind of this work was first kind of discussed in Carleo in 2017. And so really what we're doing is, so we have some exact wave function that we're trying to model with some approximate wave function that's parameterized according to some ansatz. And here, what we're doing is we're representing this phase of the wave function and then the amplitude of the wave function using an autoregressive generative neural network. And so the reason we want to do this is because autoregressive generative neural networks are really good at processing sequential data. So something like a bit string of different kind of measurement outcomes, they have some sort of kind of correlations within them. And these autoregressive neural networks are very good at learning kind of these autoregressive probability distributions, which have built into them like correlations between different sites that we want to learn. And these methods are really useful in the context of natural language processing, which I'll briefly discuss when I mention the specific type of neural network that we build our neural quantum states from. And so then the other property, oh, sorry, yeah.
Maybe before I let you get too far, quick clarification question, if you don't mind. Is the goal here to really model each and every of the possible 2 to the n amplitudes?
So indirectly, so if I go back to kind of this image, you could model kind of these 2 to the n, but the idea here is that this neural network, especially for kind of large systems, becomes a low dimensional representation of the wave function. So kind of all of these kind of correlations or the predicted outputs are sort of housed in the weights and biases that you're trying to train within the neural network. So so we would, like if you want to get the complete wave function, you can ask it to predict kind of all of the different computational basis elements. And I think like kind of indirectly without implicitly training this, I mean, in your training algorithm, it could be that kind of some subset of the computational basis states are kind of present in your training. So I think this is very common, like a lot of physically relevant states that you're studying don't kind of touch on like the complete Hilbert space. And so it also is able to kind of focus on the ones that appear in your data set. So kind of the basis states that are kind of relevant in whatever training protocol that you're trying to study.
I see. Yeah, because for 30 qubits, there are about 1 billion basis sets, and for 50 qubits, it's billions of billions, and so on. And maybe just so I follow you, is the idea here that you're doing a kind of low-dimensional sparse representation of the entire potential? Like you can generate any of them, or is it that you're going to limit yourself to a subset of them?
So it could generate all of them. So like you could, so the low dimensional kind of representation is this neural network. And so for something like 30 qubits, like the number of weights you have will be kind of less than this, than the kind of like the all of the different computational basis states. But you could ask it, so you can then like have it predict all of these different ones, but like the storage space that you have for the wave function is this kind of is the neural network, which has fewer weights than like if you wanted to do it for a 30 site model.
I see. So there's some degree of expressibility of wave functions that this can handle. And like if I gave you a wave function where all the weights were completely random, that wouldn't be something. I guess it would somehow approximate it, but it wouldn't give you the exact thing, if I understand right.
Yeah. Yeah. So I do think that there's actually been some work on this, and I believe the right people to point you to would be kind of work of Roger Melko and Juan Carrasquilla, where they study kind of like how well you can learn it if it's kind of a completely random wave function versus something that has more structure. So yes, there is an element of expressibility of these neural networks, and it's better at representing something that has structure versus something that maybe, let's say, is completely random.
Yeah. Gotcha. Okay, and that's something you just have to find out operationally, or maybe you'll get to it.
Yeah, so I think most of this is done operationally. I think that there is some interesting work, and I think this overlaps a little bit with kind of understanding the performance of machine learning algorithms theoretically versus heuristically, and a lot of the work kind of beyond the application of neural networks in the context of studying quantum systems is like this shows up also in kind of computer science, and the whole machine learning field is really being able to understand kind of the heuristic performance of all of these neural networks. So I think in some ways it's also a question that kind of like the whole machine learning community is trying to understand better, which is how do we verify and prove the performance of all of these neural networks in kind of different settings. And I think that for me, I think it's a really exciting application or question to explore as a physicist. And I think especially in this intersection between kind of quantum computing and classical computing, are there complexity and quantum advantage arguments in what we can learn using kind of quantum data versus classical data and kind of big questions like that, which I think are starting to have some focus, but there's still a lot of really interesting work that I think should be done.
Yeah, that's a good follow-up. We had Robert Huang here two weeks ago on the seminar, so very, very related. Thank you.
Yeah, no, he's doing some really interesting work on that kind of concept and problem. Great. So I think let me just kind of start off here. So yeah, like I was saying, kind of what are we representing? We're using, yes, so I think I covered this slide. Yeah, so the model that we use in our work is a transformer neural network. And this is a neural network that was developed in the context of natural language processing. And it was shown to be very good at modeling spatial and temporal correlations between kind of sentences. And if you think about kind of the sentence structures, you need to learn, if you want to predict a new word in a sentence, you're trying to understand and learn kind of what's the probability of the next word given the prior words in the sentence. And so this sort of natural language processing construction of architectures lends itself very well to kind of modeling quantum correlations in quantum systems. And so the other benefit of using a transformer neural network is that its output is complex. And so we can interpret the output of our function as being the log amplitude of the wave function that we're trying to model. And then the real part of that output is mapped to the kind of the probability distribution or the amplitude, or like the amplitude of the wave function. And then the imaginary part is mapped to the phase. So this allows us to kind of model both the probability / the absolute value of the amplitude and the phase at the same time using the same neural network, instead of using two separate neural networks to model the phase and the amplitude, which is also sometimes commonly done. And then we optimize these neural network parameters according to some cost function. And so that kind of adjusts. It tells, if I adjust the wave function parameters so much, how does that change the probability distribution? How does that change the phase? And given some kind of training algorithm, we try to optimize those two values to kind of match what we're trying to train for.
Elizabeth, could you just clarify why it's the log? What's the motivation for the log again?
So the motivation for the log, the motivation for the log is that we're able to separate out the amplitude and the phase by kind of like it allows us to split it into, like, we can just say that the imaginary part is the phase and the real part is mapped to the kind of like the amplitude / the probability distribution. If it were just kind of the amplitude, you could say that you're modeling like, okay, the real part of the amplitude versus the imaginary part of the amplitude, but it's kind of advantageous to be able to separate the two of them. And allows you, because sometimes learning the phase of your ground state wave function can be really hard. And so if we're sort of like, this strategy kind of allows you to separate them out a little bit cleaner than if you just took kind of like the complex and said it was, the real part and then the imaginary part.
Thank you.
So then we can use this neural quantum state to compute various different observables. So, we can find the expectation value of some observable by summing over kind of this probability distribution modeled by this neural network, as well as like the local observable, where the local observable is coming from kind of information about the wave function itself in addition. So that's where kind of some of this phase information comes in. And then, and so this is kind of how we'll look at, this energy optimization. And we have like one or two tricks to make this a little bit more computationally intensive and kind of reduce some of the scaling. So you're not computing an exact observable during every training step, but instead you can kind of use this generative property of the neural networks to estimate this probability distribution by kind of Monte Carlo sampling. But I'll discuss that more kind of in greater depth in the next section when I go into the energy optimization component of this neural error mitigation protocol. So now that I've kind of discussed the construction of this neural quantum state tool, now I'll talk about how we're actually training it in each of these, the steps in our error mitigation protocol. So the first step, as I talked before, is preparing this ground state on some quantum device. And then once this ground state has been prepared, we take a set of projective measurements, and then that is going to compose this measurement data set that we input into our neural quantum state tomography protocol. So the goal here is to reconstruct this wave function with a neural quantum state, so just that tool that I mentioned before, from this measurement data set that we've collected. So the step here is meant to kind of reconstruct the state that was prepared on the quantum device and translate it into this classical representation of a neural network as this neural quantum state. So kind of in this protocol, what we just want to do is get a good representation of the state that was prepared on the quantum device. And then the last step is I basically post-process this neural quantum state and fine-tune these parameters by putting it into a variational Monte Carlo algorithm, which uses the variational principle. So it's minimizing the energy of this wave function in order to get a better representation of this ground state wave function that we're interested in for the particular system. And so at the end of this protocol, we have the return is a kind of an error mitigated representation of your ground state where all of the information is stored into these weights and biases of this neural quantum state. And so, as I said before, kind of like these last two steps are this neural error mitigation protocol. So how do we do this tomography step? So we're trying to approximate the state represented on the quantum device, and that's where we use a data-driven machine learning approach to quantum state tomography, where, as I mentioned before, we take some projective measurements where they look something like this, where in our protocol, we use something that's called we named nearly diagonal. So it's mostly Z measurements, and then there are kind of like a few low weight X or Y measurements. And then we have kind of the outcomes of those measurements. We input that into an unsupervised learning task. And so an unsupervised learning task is one where you're training on data that's not labeled. So if we're training on something and I'm not telling the image that it's a cat, if it guesses that it's a cat and saying it's right. Instead, we're trying to kind of indirectly get it to know that what wave function it should model by kind of this input measurements that we're using in the training algorithm. And so what we'll do is we're going to be more specifically minimizing the statistical distance between the target wave function, the target probability distribution and the model probability distribution. And then this allows us to reconstruct the quantum state from measurements.
Could you say what's the motivation for having mostly Z's and only some X's?
Yeah, so the motivation for that is because when we input the measurement outcome into the neural network, the input is given in the kind of computational basis. So if we have a lot of X measurements, let's say, we have to do kind of like, let's say there's 4 here, we have to like transform those measurements into the computational basis state. So if we have a lot of really high weight measurements, then that increases the computational overhead because it needs to do this like change of basis kind of for each measurement that we input. So we try to keep that change of basis limited to kind of only a few qubits that needs to be transformed into the Z basis instead of kind of like the whole bit string. So that is kind of one of the computational cost elements that we had to consider when we're kind of composing these measurement data sets.
So do you mean change of basis on the quantum device before the measurement, or do you mean something in post-processing?
So afterwards. So after it's like the input to our neural network, it needs to be in the Z basis. So if we have a measurement that was given in the all X basis, then we need to kind of transform that into the Z basis.
Okay. Maybe I missed it, but what does that mean?
Oh, so I mean, like, it's just like the state that like is the outcome. It needs to be like each of the qubit. Like if it's a 0 measurement in the X basis, then it needs to go to being like a 0 + 1 in the Z basis. So like you have to do this like vector change of basis in order to like input it into the neural network.
Oh, I see. So you're assigning, so you're saying if I get a 0-bit string for an X, I turn that into a 0 + 1 in the ket representation, and I need to do that classical. Okay, got it.
Yeah. So changing that for something that has like a high weight of X's, especially for kind of a large system, would increase the cost of the tomography protocol.
And what would be the kind of, maybe we'll get into this, the quantum experiment cost, because some of these measurements might be commuting, so you can take them in one shot, but some of them may not be.
Yeah. So we yes, I'm trying to remember what we did. So I think that we did take that into account. I mean, at the end of the simulation, I think we only had I want to say there were like 10,000 measurements. So I think there were maybe like 10 or 15 different measurement bases that we took measurements in, and then there were maybe like 1,000 measurements per measurement basis.
I see. Across how many qubits?
So I believe for the lattice Schwinger model, so for something that we studied with 8 sites, I believe we took 15 measurement bases, and then I think that would be on the order of like 15,000. And then for the lithium hydride, I think we also took something like 10 measurement bases and maybe like 1,000 per. So it was like about 10,000. So it's sort of like, it's not, it also is sort of model dependent based on kind of like the complexity or the type of the Hamiltonian itself that you're trying to measure changes, what types of measurements might be necessary. Yeah.
I see. So very, very few by this estimate, I guess. Yeah.
Yeah. Yeah. Mm-hmm.
Okay. Thanks.
Yeah. So how do we actually measure the statistical distance between these two target probability distributions? So the way that this is kind of done convention is using the Kullback-Leibler divergence. So effectively, if you look at this this equation, if your model probability, so this p lambda, is equal to the target probability p of x, then that value is 0. And so this kind of expression, you want to try to minimize it to get to 0. But one thing I'll note is that we don't actually need the whole cost function, because this target probability is constant throughout training. So when we take kind of the gradient of this cost function, which is what we're really using in training, this p of x log p of x term is constant. So we don't need to look at that. Instead, we just look at this kind of p of x, or this minus p of x log p lambda of x, and that is called the cross entropy. So it looks like this. So instead of this whole KL divergence, we just look at the cross entropy, and then we can estimate this cross entropy because we don't have access to that target probability distribution. We model it using these measurement samples that we took from the quantum state prepared on the device. And then, so effectively what we're trying to do is then just minimize the cross entropy between this target and model probability. And it looks like this, where I've just included this B here, where kind of trying to let you know that inside each of these X, there's also implicit information about kind of what that basis was measured in. And like I kind of mentioned in the question earlier, which is that you have to transform these measurement bases. So we're also kind of trying to model the probability of of all of this, and we're getting also additional information based off of the basis that you're measuring. And then we update these parameters using stochastic gradient descent. And so this quantum state tomography protocol was introduced by Giacomo Torlai in 2018 with co-authors. And so then there's been some really interesting work, and this has been a really neat tool, which takes this machine learning approach to kind of state reconstruction. So the second stage of our error mitigation protocol is this energy optimization using variational Monte Carlo. So the variational principle tells us that an exact ground state energy is upper bounded by this minimized variational energy. So this variational energy is computed from some kind of variational wave function ansatz, and you minimize these parameters in order to get kind of an approximation of the ground state energy, and also kind of getting some sort of estimation of the ground state wave function itself. And so again, we optimize these neural network parameters according to the energy cost function. which looks something like this, where we take kind of a similar trick by kind of generating a measurement data set in order to model this probability distribution of your model, so this P of lambda. Then it becomes a sum over kind of all of these local energies of the samples that you have in your cost function or in your generated measurement basis. And so, we can compute this local energy with this following equation. And then as I mentioned before, we want to use kind of sampling in order to estimate the model probability to kind of constrain some of the complexity of estimating the energy at each step. So when we use this Monte Carlo sampling to estimate the energy, we can generate samples via this generative property of the neural network, which allows us to sample from the probability distribution modeled by the neural network. So not all neural networks do this, and if it didn't have this property, what we would have to do is generate samples from some external probability distribution. And it's much more advantageous to be able to sample from the probability distribution of the model itself. And then again, we're kind of minimizing this via stochastic gradient descent. And in our neural error mitigation protocol, we're initializing this neural quantum state. So the starting point for this variational Monte Carlo algorithm is from a neural quantum state that was kind of pre-trained using experimental data. So one additional part we use.
Questions,
Yes.
Elizabeth, from the audience.
Okay.
First question from Merkaba. Does the method require, does it only work if you first know the target probability distribution of your ground state wave function?
So you don't need to know it exactly. You just need to have the ability to take measurements from it. So you need to have access to it, but you don't explicitly need the exact probability distribution. So essentially what I'm trying to say is you need access to some sort of measurements in the tomography scenario in order to kind of learn the state in that training step.
What if the state is prepared perfectly, but the measurements are faulty?
So this would also work in this context. So we're not trying to target a specific noise model. It could be that your measurements are faulty. It could be that the state prepared is faulty. So the tomography would be learning some of these faulty measurements, but then during this energy optimization, so in this VMC step where we're error mitigating this ground state, it would be able to kind of improve the representation, even though its starting place might have some kind of faulty measures, whether it's measurements or kind of the preparation of the state itself.
And wouldn't the potentially faulty measurements create a biased estimator of your energy? So you could be optimizing on a biased estimator, so you might not find the true. Do you know what I mean? Is that an issue?
Yes, I missed the first half of that sentence. If you could just repeat.
Oh yeah,
for me, that'd be great.
Yeah, could you just clarify when you mentioned about optimizing? If your measurements are faulty, they might create your estimators might be then biased. So if you're trying to estimate the ground state energy, you might get the wrong energy, or maybe there's a skew somehow to what is the lowest energy. You might end up with different states. So anyway, does that come into play here, or have you thought about that?
Mm-hmm. Yeah, I think possibly, I think actually the next slide might answer this, because we did see this. It wasn't explicitly a bias in the energy estimation, but it was during training. Sometimes we found that we got stuck in, let's say, a local minima. And so it was hard to get out of that, because when we were sampling from this probability distribution, it was biased towards something that was maybe the dominant contribution to some ground state, and so it wasn't able to kind of jump out. So we were kind of, it kept biasing itself into this little minima. And so what we did is that we used a trick from kind of machine learning, which is minimizing the L1 norm, which minimizes the sparsity of your, discourages sparsity in early training. So in this context, we saw that, something like the Hartree-Fock state in quantum chemistry is the dominant contribution to your ground state. And so if our model very early in training was only modeling this Hartree-Fock state, it became difficult for it to get kind of the subdominant amplitudes. And so we introduced this small regularizer in order to kind of push up some of these additional computational basis states, trying to ask it to say, just try to learn it for a little bit. And then we kind of weaned it off and took it off. So then after kind of discouraging the sparsity, we then said, okay, now do kind of completely just energy optimization. And we found that that really helped us get to kind of this global minima, or, a very good representation of the ground state itself. So it, like, our cost function at the end of the day was this one part kind of energy estimator, and then we kind of introduced our own bias if where through this regularization, which we could then control throughout training according to some schedule. And this allowed us to kind of ensure that we weren't going into some local minima too quickly, and we were able to kind of counteract some of that sampling bias that may have occurred.
Okay, thanks. I'll let you proceed. And, there's a couple more questions, and I'll maybe, just in the interest of time, I'll leave them to the end of the talk. And folks, feel free to bring up these questions back up anytime later, or maybe at the end of the talk. Thanks, Elizabeth.
Okay. Great, thank you. Yeah, so then basically here, just one note I want to say is that kind of the number of samples that you use in this cost function is kind of be referred to as the batch size, which in some of the later results, I'll discuss a little bit more. Basically, you can more accurately estimate what this cost function is by increasing the number of samples that you have, or, if you have fewer samples, there might be a larger variance on this cost function. And so that can kind of play a role in training as well. So to give you a brief summary, these neural networks are really good approximations of quantum wave functions. They show up in natural language processing. And we train kind of with two different objectives. One is state reconstruction, and one is ground state approximation. And then this neural error mitigation protocol is combining these two, first learning the state via tomography, and then improving it using VMC. So now let me show you guys some results. We study two different models. The first one, we study LiH ground states, which we model where we use our error mitigation protocol on a quantum simulation from a hardware efficient variational circuit. So kind of based off of this work right here, this hardware efficient variational quantum eigensolver problem. We show two results, one for simulated using device noise, and one, so basically we did this on a device, and then the second one is with depolarizing noise, simulated numerically. And then the second one we did was the lattice Schwinger model, which was done in this paper right here, the self-verifying quantum variational simulation of lattice models, where this was a variational analog simulation. So it was modeled on kind of the operations that you could do on with a trapped ion quantum simulator. And we did this simulated numerically using depolarizing noise. So here are the results for lattice, first thing I want to talk about the Hamiltonian. So if we map our problem to 4 qubits, you go from this STO3G basis into the second quantized Hamiltonian. And this gives you kind of these creation and annihilation operators on different orbitals. Then we look at the parity transformation, takes us to a 6 qubit Hamiltonian, and then reduce it by 2 qubits using a spin parity symmetry. And so, as I mentioned before, we use this hardware efficient variational circuit with 2 qubit entangling gates and single qubit rotation gates. We have one entangling layer, which gives us about 20 parameters. So here are the results. So in the left in the big, we have this energy plot as a function of bond length. So kind of as a separation of these two molecules. In the top right corner, we have the energy error, and in the bottom right-hand corner, we have the infidelity. So the VQE results are shown with these blue triangles. The tomography results are shown with these green circles. And then our final neural error mitigated state is shown with this red diamond. So we see here VQE is able to capture qualitatively what's going on in the energy curve, except if you look at the top right corner, the energy error is still kind of just below 10 to the minus 1. So there's still a lot to improve, especially if we're trying to reach chemical accuracy. So the next step here is, these tomography results. And so here, what we just want to see is that tomography lines up on top of VQE. So we want to see, is this tomography protocol learning fairly well the state that's prepared on the device? And we see that it is, especially if you look in this bottom right-hand corner of the infidelity, which, because we simulated this variational quantum eigensolver numerically, we're able to kind of look at the infidelity of this result. And we see that there's like a very strong overlap between this tomography, the neural quantum state trained with tomography, and the state that we obtain at the end of VQE. And then after training with this energy optimization, we kind of were able to really improve the energy error, such that in this all of the data points, the means were below chemical accuracy, and we have really low infidelities on the wave function itself. And so just to give you a sense of really kind of what's going on in one of these data points, which is what's going on with this kind of state picture. So let's look a little bit more into this quantum state reconstruction, where we can see here VQE is modeling maybe the first two computational basis states. In the top row, we have the probability, and in the bottom row, we have the phase error. And we see that, VQE is maybe getting here the first three dominant computational basis states, fairly accurately, but kind of after that, there's less accuracy. And then this tomography is really learning that probability distribution really well. But it kind of, if we look down on the phase, this tomography is not maybe getting the phase very accurately. And so it's after we do this neural error mitigation protocol, we're really able to fine tune the model of this probability distribution and also get a really low error on the phase, specifically for those computational basis states, which have more dominant probability probability values, kind of notably above 10 to the minus 5. So let me also show you the results from an IBM. So we did this on one of IBM's 4-qubit devices. Here, our VQE results aren't as good. There's just more noise in the model, and that's kind of what we expect. So now we don't have access to the state in VQE itself explicitly. So you can kind of think about, especially in this bottom right infidelity plot, this neural quantum state tomography as being kind of an estimator of the state that's being prepared on the device. And so here we have kind of an infidelity between 1 and 10 to the minus 1, which is there's a lot of room for improvement there. And it's after we train with this neural error mitigation protocol that we're really able to get very low energy, so below chemical accuracy and very low infidelities for these sites. And I'll briefly just show you kind of the same plots. We see very similar things where we're able to model the probability distribution after this with this error mitigated state very well as getting good estimations on the phase.
This is a numerical noise model.
This one?
The one after that.
This is, no, so this one is one data point from the where tomography was trained using measurements on a device.
I think I see. Okay.
So this one we don't. So in the prior to the slide 2 before this, we had the VQE probability distribution because we had access to it numerically, but now we don't. So now it doesn't show up here, and you kind of have to treat this tomography as maybe an approximate, representation of what's going on the device.
Okay. Gotcha. Okay, good. Thanks.
Yeah. So then the other model that we studied was the lattice Schwinger model, which is a toy model for quantum electrodynamics in 0+1 dimensions. So the first term in this Hamiltonian is a creation and annihilation term for electron-positron pairs. The second one is a bare mass term. And then the third one is a coupling to an electric field. And so what we do here is we want to study this Hamiltonian as a function of the bare mass. And that's because there is a phase transition in the thermodynamic limit around mass of equal to approximately negative 0.7. So when we look at this quantum simulation, we want to observe kind of how well are we able to model and identify the signatures of a phase transition that would show up in the thermodynamic limit. And the quantum simulation that we model this on is, as I mentioned before, kind of this variational quantum simulator model where we have, instead of a 2-qubit entangling gate, we have an n-site entangling gate. And then otherwise it's very similar where we have single qubit rotations and then this, entangling layer. And then we simulate this using depolarizing noise. So here are our results. In the top left-hand corner, so in figure A, is the energy. In the bottom, in B is the order parameter. In C is the entanglement entropy. And in D is the infidelity. And so what to note here is that VQE kind of very qualitatively captures the exact ground state observables. So we see sort of general trends, but they're not very accurate. And it's really after this neural error mitigation procedure that we're able to really get very accurate estimations of all of these observables. And what's pretty neat about this is that even though we're just optimizing the neural quantum state, this tomography state using energy, so we kind of expect to have good representations of the energy because that's what we're directly optimizing. But we also get really accurate estimations of things like the entanglement entropy and the order parameter, which we aren't directly estimating. And that really is because what we're doing is we're fine tuning this wave function underlying the whole in the form of this neural quantum state. So in this image D, the infidelity of our wave function is going down, and so we're getting a really accurate wave function approximation, and so that allows us to get better estimations of these complex observables for like things like entanglement entropy and order parameter, and especially for the order parameter, as if we scale this up to larger system sizes, that's going to tell us more about kind of this phase transition, and having a really good estimator of that order parameter is important when you're studying these phase transition systems. And so again, kind of like a look at this quantum state reconstruction. And so here it's for a mass value of negative 0.7 for this 8-site model. And here we kind of see very similar things that we saw in the smaller model with LiH. So VQE kind of qualitatively measures generally the computational basis states that have some sort of more dominant contribution, but it's not very accurate. And then tomography sort of overlays on top of that with some error. And then finally, this error mitigated state is much more accurate for both the probability distribution that it's representing as well as the phase. And so, as I mentioned, so we can also study this lattice Schwinger model for various different system sizes. And what's beneficial about this model is because it's a lattice model, so you can just increase the system size and it doesn't increase the complexity of the Hamiltonian. So like we just obtain kind of like a linear term growth in the Hamiltonian instead of scaling to some of these larger quantum chemistry molecules that are more complex as they get higher. So there's kind of an additional complexity that shows up when we're trying to study larger like electronic structure problems. Here we can study this simply by increasing the number of terms that we have. And so we're able to show that kind of for system sizes up to 16, which is really what we were able to look based on kind of the classical resources that we had for simulating these systems using depolarizing noise. We see that we're able to kind of maintain about 2 orders of magnitude in scaling. And here I'll also note that the neural network that we use doesn't grow. So in each of these steps, we weren't kind of training it on a neural network that had more and more expressibility and more hidden layers and more kind of internal dimensions. We kept the neural network itself constant. besides kind of just increasing the number of inputs that we had based off of the size of the system. And so we're able to kind of like get pretty good scaling for various different batch sizes. So as I mentioned before, kind of like looking at these different batch size numbers, we, with higher batch number of samples in your training algorithm, you're going to get more accurate results. And here, even for something of a smaller batch size of 2 to the 8, we were still able to get, about 2 orders of magnitude improvement for both the energy error per site as well as the infidelity. And so the last thing that I want to show you is also kind of studying this model as a function of depolarizing noise rate. So what we can do is we can adjust kind of the noise rate in this simulation and see how well our model behaves. So the way that I like to look at these plots, so on the left, we have the energy error and fidelity in the middle, and then the purity on the right. And so when our depolarizing error rate is 1, it's a maximally mixed state. So the state we're getting out and we're training from is one that has a very not a lot of information about the quantum simulation or the ground state that we're trying to model. And then when we look at a depolarizing error rate of 0, that's when we're looking at kind of something that has no noise. So it has kind of as in the most amount of information about the state kind of given the protocol. And so we see that kind of across as you go from a depolarizing error rate of 1 to 0, there's sort of a transition between where our model does, well, so we're still able to improve things, to where it does better on the left-hand side of this plot. So there is a point where the neural error mitigation procedure is reaching better estimations of the ground state itself because it's learning something from the quantum simulation algorithm and the data that it's getting from. So I think that that's something that's really interesting. It's not just kind of, it's achieving something from being able to start at kind of a good place via this tomography and getting kind of information from the quantum data. So thank you very much. This is just my summary. So this is neural error mitigation method. It combines these near-term approaches for quantum simulation with classical machine learning tools that have been developed to study quantum systems. Our protocol is agnostic to hardware and noise, and we show that it really are able to improve the results to really yield really small errors in energy, low infidelities, as well as accurate estimations of entanglement and entropy and order parameters. And so I'd also like to thank kind of all of my co-authors, as well as all of the support that we've had for this project. It's been really kind of very exciting and a really wonderful project to work on. So I want to thank them as well.
Elizabeth, thank you very much for the very nice talk. We have, folks, this is a great time to post any final questions you have for Elizabeth, and I can see a few in the chat already. Feel free to add more questions and we'll bring them up to Elizabeth now.
Great, yeah.
So, so the first question was, let's see. The energy optimization process with Monte Carlo will lead to a correct ground state as part of the variational process, even if your initial probability distribution, distribution is not correct. Oh, and we actually can bring up the questions at the bottom of the screen. That's great. So I think this might be more of a statement than a question, but any quick takes on that, Elizabeth?
I just have to change my screen for a second just so I can see the question. Yeah.
I'll read it back to you. On the energy optimization process with Monte Carlo is going to lead to it's not really a question, actually. You know what we're going to do? We're going to come back to that. Merkaba, clarify if you want. Let me go back to the next question by Shashi. How difficult was it to implement this transformer in PyTorch? Could a recurrent neural network be actually used in place of this transformer, as they both deal with sequential data?
Yeah. So the transformer was, I mean, I think there's always a bit of a learning curve when kind of learning to build a new architecture. So I think that there's definitely some work that needs to be done to kind of like figure out what's going on and looking at it. We actually have published our our code on GitHub. So if you search kind of 1-qubit neural error mitigation on GitHub, you can see kind of our code, and the transformer that we use is in there. And yes, you could use a recurrent neural network. And I think that that's also a really excellent choice in this protocol as well. Like you said, because it does deal with sequential data. And so there are a couple of different, really great generative autoregressive neural networks that you could use. We just happen to use the transformer in our model. But yeah, absolutely right. There's a lot of different ones you could use, and you could use an RNN for sure.
Great. All right. So this time, a question from. Okay, sorry. There's a lot of chat streaming in at once. Are there alternatives to this neural approach? Bayesian algorithms, genetic evolutional algorithms, etc. I guess this is probably a question about the benefits, pros and cons of this versus potentially alternative approaches.
Mm-hmm.
And what is the resource requirement that goes along with the training?
Yeah, so I guess to give everyone a sense of kind of what type of training we did. So even for kind of the n=16 model, we used a CPU. So we weren't using a GPU to model this. And I think it took on the order of 2 minutes to train. And so, it could be very easy for us to make the neural network really, really big and kind of put it on like a very powerful chip, but we really wanted to make it something that could be done on your computer. And it is something that, so while, and like the measurement training, so something like 10,000 measurements is not kind of like that much in the grand scheme of things. And then when it comes to the VMC, choosing something that's like 10 to the 8, which is like, 256 measurements per batch size. That's not that computationally intensive either, but you can always make it more accurate by increasing the measurement data set. But this is something that like it could be done just on your own laptop in kind of the order of like a minute or two. And so I think that there's a lot of utility in that as well, being able to kind of error mitigate something kind of in a few minutes. And then you also have this saved neural quantum state on your device. So then kind of you can save these weights, and then you can use it in the future. So it could also be used if you just want to study or if you just want to extract this ground state for a different problem. And so I think there's also utility in kind of having this classical stored error mitigated state at the end of the protocol.
All right. Folks, if I missed your question from earlier, bring it up in the chat. I think the last question, and it's a bit related to the last one, was how much time does the NQST step introduce?
So we, so I believe for the lattice Schwinger model, it was probably 1 minute, and then VMC was maybe another minute. I will say actually in the supplementary information of our paper, at the very, very end, there's a table that includes all of the hyperparameters of the models we use, and it also includes the timing for the tomography step and VMC for kind of all of the models that we studied. So, and I believe for LiH, it was actually a little bit more. Part of that is because like this LiH Hamiltonian has a lot more terms and a lot more like diversity of terms than the lattice Schwinger model. And I believe that, maybe that was potentially 2 minutes or so, but to check, there's that table in the back of our paper, which I think will answer your question.
All right, great. Well, thank you for answering that, folks. Thank you for the many questions during the talk. Elizabeth, thank you for accepting our invitation and for the very nice presentation. This talk will stay recorded, so you can go back and rewatch it and come review the very nice results by Elizabeth. And before we close out here, Elizabeth, don't know if you want to share any final words or comments with us.
No, just thank you everyone for tuning in. Thanks for the great questions. I'm really excited to share this method with all of you, so I hope you enjoyed it and I hope you learned something. Yeah, tune in for more Qiskit seminars in the future.
All right. Well, folks, you heard Elizabeth. With that, see you next Friday at noon Eastern Time. Have a great day.